In this lecture, we are going to be talking about decision trees. So what's the big idea with a decision tree? We can repeatedly split the records into two parts so we can achieve the maximum homogeneity within the new part. And so we'll talk about how we can do this here in a few minutes. But first, let's talk about what a decision tree is. And so decision trees are composed of nodes, branches, and leaves. Each node represents an attribute or feature. Each branch represents a rule or a decision, and each leaf is going to represent an outcome. Then the depth of the tree is defined by the number of levels, not including the root node. So here's an example of what one might look like. We're going to use a layered splitting process, and at each layer it's going to try to split the data into two or more groups so that the data falls into the same group are going to be most similar to each other, which is called homogeneity, and data that are in separate groups are as different as they possibly can be, and this is called a heterogeneity. So again, level 0 is shown with the squares, and then level 1 is indicated with circles, and level 2 is shown here with the triangles. So once again, this is an example of a two-layer decision tree. The goal of our trees is to classify or predict an outcome based on a set of predictors, and the output is a set of rules. So what are some examples of where we can apply decision trees? We can use it to classify a record, such as if a customer will accept a credit card offer or if they will not accept it. Another example would be if income is greater than a certain level, education is less than a certain level, and then our family is smaller than a certain amount, then your class would be equal to 0, which in this case would indicate that we have a non-acceptor of our offer. There are also different types of decision trees, including cart decision trees or just trees. When you hear these, they all mean the same thing. So you can fit a cart, you can fit a decision tree, or just trees. And they're all the same thing. We will talk about what a cart model is here in a little bit. And the rules are going to be represented by a tree diagram. And we will see how that works. One thing I will note here as well is that we will be able to apply a decision tree to not only categorical data, but we can also use continuous type of variables. And we'll talk about that here in a little bit. Now let's actually talk about how we fit the rules through a process called recursive partitioning. So recursive partitioning refers to the process of segmenting the responses into groups that are as homogeneous as possible and maximizing the differences between the observations that are in different groups. So each group has members that are as similar to each other as possible, but those members are going to be as different from the members of other groups as much as possible. So successive splits will produce a branch structure of rules and groups that are known as a decision tree, which once again is going to be that actual model of our data. The splits are going to be binary, and the reverse of splitting is going to be pruning. So when we go forward, we split the tree, and then when we go backward, we are pruning the tree. And we will see that later, and we'll talk about how we can do that here in later slides. But once again, a tree is going to help us to interpret the associations within our data. So to show you an example, here we're trying to predict whether an individual is a homeowner or not. We could use various factors such as income, education, number of family members in the household, and so forth. So we can start by creating our splits. The first split that we see here is income, and then our first group coming off of income is split again based off of education. And when we look at those splits, the split that went off to the left is further split by family and then income. And then on the right, we see that it once again got split by income and so forth. So this is an example of what a decision tree might look like. So what are the recursive partitioning steps? First, you pick one of your predictor variables, x. And then you pick a value of x sub I, let's say s sub I, that divides the training data into two but not necessarily equal portions. Then you're going to measure how pure or homogeneous each of the resulting portions are. And in this context, pure means that they're containing records that are mostly within the same class. So if a group has mostly non-homeowners, then it's going to be highly similar or homogeneous. But if there's a mix of homeowners and non-homeowners, then it's going to be a little bit less clear. And so our algorithm is then going to try different values of x sub I and s sub I to maximize our purity in that initial split. So it's going to look at which one gives me the best split so that I can have the most purity within my groups to, once again, maximize our purity in our tree. And then after you get that maximum purity split, it's going to repeat the process for a second split and so forth. And so that's how we end up growing our tree. The way of selecting the most important variable in constructing a decision tree is called the splitting criteria. So what are the different criteria that are used to split trees? So different models use different criteria, and different algorithms that are fitting our decision trees depend on the parameters of what we're doing. So once again, if we were to use the CART method, it's going to be more focused on practical significance of the splits and looking at the improvements in the predictive power. CART is one of the algorithms that we will be able to apply in our program. We also have the CHADE model, which considers the statistical significance of the split, but it can be easily over-influenced by the sample size when selecting a split. And we also have another algorithm called C4.5, and then it has a newer iteration which is called C5.0. This considers the gain ratio and tends to lead to smaller decision trees. And we'll talk about the gain ratio here in a few slides. But it is best to examine trees created from several different techniques because there's not necessarily going to be one best technique for every type of data. So you always want to try a few different trees, algorithms to see which models your data the best. So here we're going to have an example where we look at homeowners with riding lawnmowers versus homeowners who do not own a riding lawnmower. And the goal is to classify 24 households as either owning or not owning a riding lawnmower. And we have two predictor variables of income and lot size. So this is what our data looks like. It's a collection of our observations, the income, lot size, and whether or not they own a riding lawnmower. So let's talk about how you actually go about the splitting. First, you are going to order the records by one variable. For this example, we will use lot size. Then you will define a midpoint between the successive points. So let's look at the first midpoint for lot size here, where the two smallest ones are 14.0 and 14.8. At the midpoint between those two is 14.4. So you're going to divide the records into those with lot size greater than 14.4 and those less than 14.4, and then you will look at how that split does as far as evaluating the purity of the groups. After evaluating that and determining which is good, you're going to try the next split, which is 15.4. And so that is halfway between 14.8 and 16.0. So you're going to see how pure that split is. And it's going to be, and you're going to continue to iterate and look at all the different splits along that one variable to see which one produces the most pure differentiation within your groups. So as far as categorical variables are concerned, it's going to examine all of the possible ways in which your categories can be split. For example, if you have the categories A, B, and C, they can be split 3 different ways as you see on the screen. Now, with many categories, the number of splits can be pretty big. So that's going to be something that we need to keep in mind, but with today's computing power, it can be easily managed even with the most complicated type of categorical variables. But know that there will be many more splits as you have more levels or categories within a variable. So now let's look back here and see what's going on when we look at our first split with this particular data set where we are trying to identify owners of riding lawnmowers versus non-owners. The solid dots shown here are the owners, and the ones that are not solid are the non-owners. And we're looking at lot size and income as our two axes. And so it turns out that the first split happens at lot size equals 19,000. So the rule is anything above 19,000 is categorized as an owner of a riding lawnmower, and anything below 19,000 is a non-owner. So you can see why the algorithm might have chosen this, because if you look at it, you see that when the lot size is above 19,000, most of them actually are owners, and then when you look below that, most of these are non-owners. Okay, so that'll be the first split that is generated, and it's based on which line, if you were to draw a line along the lot size axis, would give me the most pure, meaning the highest percentage within the category being the same, so the highest percentage of owners. So if I draw this line here, an observation above the line will be in one group, and observations below the line are going to be in another group. And so it creates the optimal split that has the highest purity. Now the second split comes at income equals 84,000. So now what it is saying is that it now has three groups. So those that are above 19,000 square feet for lot size, irrespective of income, are going to be labeled as owners of riding lawnmowers. And those that are less 19,000 but have an income less than 84,000 will be in the group on the lower left hand section. That group is going to be considered non-owners because most of these are non-owners. You can see that they are not solid. There's only one solid, so it's not 100% pure, but the vast majority here are not owners. And then when you look at above lot size 19,000, you see that there are two observations, and then so that there are two owners of riding lawnmowers. So again, here if income is above 84,000 and the lot size is less than 19,000, it's still going to categorize them as owners. And here the purity measure in this group is 100%. So that means 100% of the observations in that lower right hand square are going to be owners. And so if you can see what we are doing here, all we are doing is we are splitting up the space between lot size and income to try and create groups within the space to identify individuals who are owners and are not owners of riding lawnmowers. So if you were to allow this algorithm to continue, you would see that after all of the possible splits, it would come up with this view here on a decision tree. And it would create all of these different groups. And you could see a tree that would identify the space that we would see in here. And that would then again identify what each area would represent. And again, each area is going to take a vote. So whatever the majority of the observation in a particular segment is, that's going to vote for a class. And whatever the majority is within that group, that will become the assignment for anything that would fall within that group. Now, in your programming, you can actually choose what you're going to set the majority at. So you can do a fundamental 50-50 split, you could do a super majority, or whatever. You can set that particular threshold for at what point does a particular segment vote a particular way. There are two metrics that we're going to use to assess the candidates for splitting. The first criterion is G2, which is also known as entropy. It is based on a likelihood ratio test for the individual splits. Again, it is looking at the change in the entropy, and the entropy is the change in the negative log likelihood, often referred to as negative L, over all of the responses. It's going to be very similar to variance. G2 is just going to be twice the entropy, so it is represented with negative 2L. So here, the larger the G2 value is going to be, the better it is. So effectively, you're explaining more variance with a higher G2 variable. The second criterion is the log worth, which is based on the p-value for a Pearson chi-squared test for independence between groups. The p-values may vary by many orders of magnitude, and the solution to that is to transform these variables by using the logarithm. Remember, when we take the log of a variable, the extreme outliers or larger variables are going to become condensed and get a little closer. So this transformation is going to produce a negative number, and larger log worth values are going to be better. So this is going to indicate greater significance. Going a little bit deeper into this measure of entropy, to give you some intuition about what exactly it's measuring, one of the most popular measurements is going to be entropy. This is the formula of how you compute it, where P is the proportion of cases out of the M in the rectangle that belongs to class K. So basically it's looking at the percentage of purity. What percentage of the observations belong to that same class? And the entropy measure is going to range between 0, which in this case will be the most pure, which means that everything belongs to the same class, and the log squared of n, which again would equate to equal representation of the classes. So if you have half that are in one class and half that are from the other, but they belong to the same split, that would not be a very good split to use. So let's talk about entropy within the context of information gain. The concept of having a single class per split spread across our data set is known as information gain. In this example, on the left-hand side, we see a scenario where it has low information gain, and then high information gain is in the situation on the right. The gist of it is that looking at the percentages that are pluses and minuses, the one that we see here in the second split from the left has almost an even mix between the two. So there's not much gain that we see when we're trying to differentiate between the positives and negatives here. It's much higher information gain in the split that we see here on the right because we have more purity. So on the left, we have mostly positives, and then on the right, we have mostly negatives. So if we were to choose a split where each output has a mix of classes, depending on the input of data, then we really have not gained much information from the split that we see here. So we do not know any better whether or not a particular node or feature has an influence in classifying our data with the low information split. So on the other hand, if our split has a high percentage of each class for each output, we've gained information from splitting in that particular way using that feature. So it gives us useful information in our classification. So how do we go about actually calculating this split metric? In this example, we're looking at automobile data where we're trying to classify vehicles into categories. The partition platform within statistical software programs is going to find a set of cut points for continuous variables and look at the groupings for categorical variables. In this case, the width is going to be a continuous variable. So it's going to look at the x values that best predict the y value by exhaustively searching all possible cuts or groupings within that width variable or width of the car. And it's going to examine that in this case by looking at what the log worth is at a given split. So imagine here there are different splits along the x-axis that you can cut with that. And it's going to identify the one that has the highest log worth, which in this case will be around here where you see this blue line. So after evaluating all the splits, it will gain just through, and I go through and just identify the highest and then use the highest log worth as a split for the width. Similarly, if we are looking at RPM and max horsepower, it would apply the same process for that variable to identify the maximum log worth along the path. And it happens to be right about here, so we would make that split here. And it will repeat that for all the different predictive variables that we have in our data set. So again, if two were looked at right now are the RPM, and then the one before it was on width, here both of these are shown with their splits, and then the output that we get from jump is what we see right here on the right. So in this case, the categorical response was vehicle category, and the first independent variable that was considered was width, or the size of the car, and all the possible splits using width are considered, as we discussed earlier. And then the cut that creates a larger separation in the response is the chosen variable. In this example, the split is put into cars that are less than or equal to 69, so and those that are above. So that is the cut point that we see over here on the right. So those that are two groups will be created using the width. That's going to compare the candidates that are the best split, and then it's going to be determined for each independent variable. In the comparison depicted here on the left, the best split for width results in greater separation for the response level than we see for RPM max horsepower. And we can see that by the log worth. So remember, we saw earlier the log worth with much higher for the split of width, which means it's explaining more of the variability than we did with the RPM horsepower. So you can see it has a lower log worth, and that we can see here as well. We can see the G2, and the G2 and the log worth are much higher for width than we see for RPM max horsepower, which is what we see over here on the top. So the one that has the highest value is going to be our best predictor, and it's going to lead to our first split in our decision tree. Before the first split, all the observed values are sorted based on the values of the vehicle category. So we can see here on the right, and the vertical axis represents the margin of probability of each value. After this first split, a vertical line appears that indicates what groups are formed by the split. And these groups are labeled with the variable, which in this case is width, and then the level of the split within the groups, as we see here with the division at 69. The appropriate conditional probability is marked by each of these horizontal lines. Then the actual coordinates of the categorical observations are random as long as they remain in the correct rectangular area of a plot after they are split. So basically, what we are doing is we are creating the split here with width. And then it's calculating these conditional probabilities which align to the type of vehicle that is going to be assigned. And then it's going to use that label for those groups. The splitting process is repeated within each partition. So we have these two partitions, those greater than or equal to 69 in width, and those less than 69. Each possible grouping in the two levels is examined for the greatest separation of responses. This is done for each independent variable. Then the best splits for all of the independent variables are compared with each partition. Finally, the best split for each of the two variables are then compared, and then we move forward with the tree generation. And so we see here those that are less than 69, the best split here is going to happen at engine size, and that has the highest G2 and the highest log worth. And over here we see what's happening at passenger capacity for that group. So this will be the next leg in the split for this branch of the tree itself. So let's go back to our lawnmower classification example to try to put together some of these concepts that we have discussed and what's happening with our decision tree. So the first split that we saw was the most optimal for lot size, and those were if the lot size was over 19,000 or not. So that was the first split that we saw. Then the next one was based on income, whether it was greater or equal to 84,075. And so now we see here on the left, if the income was higher, then those who were going to be owners, and then the rest would continue to split. And what we would see is that it would continue to expand until you get an optimal solution before you start to prune that decision tree. And here again, what we are seeing is the split points become nodes on our tree. Those are the circles with the split values in the center, and the rectangles represent our leaves. These are the terminal points which have no further splits after that point. The classification values are noted for whatever falls within that leaf. The number on the line in the nodes indicates the number of cases, and you read down the tree to derive a rule. So for example, if a lot size is less than 19 and income is greater than 84.75 thousand, then they're classified as an owner. Now let's talk about determining the leaf node label. So each leaf node label is determined by voting of the records within it and by the cutoff value. And so the records within each of the leaves are from the training data. The default cutoff value is 0.5, which means that within the leaf, one class is more than 50%, so it's labeled by the majority class. So if a leaf is 51% owners, then whatever falls into that leaf will be classified as an owner because the majority is what falls into the owner category. If you use a cutoff point, for example, 0.75, it's going to require 75% of the records in that leaf to be one class to earn that label. So again, go back to that example. You would need 75% owners or more to be classified in that leaf for you to determine that anything that falls within that leaf would be an owner. Otherwise, it would be marked as 0, or in this case would be non-owner. So this is what you would see after applying all of the different splits. The top part is what we saw in that earlier diagram where we saw income and then lot size on the X and Y labels with the different splits. So this is a representation of what the tree would look like. Now, it is likely that the tree will be overfit, so there's going to be some pruning that we would need to do. So to talk about over and underfitting a little bit more, if you recall from our earlier conversations, overfitting refers to a model that learns the training data, and the data that is used to learn and train the model so well that it has problems when it needs to generalize on new unseen data. So it's going to be learning both the signal and the noise. And so in a classification problem, that might be what we see in the graph over here on the left. We would have an example that's underfit here on the left, and here on the right we would see a model that is overfit. Okay. And so the graph in the middle is going to be somewhere in between, and that's likely going to generalize much better than either our overfit or underfit models. The regression type of problem will be looking like this, where the red line would represent an underfit line up here, and then the green represents the actual relationship itself. So this is just underfit, on the right is overfit, and in the middle once again is just right. So going into this a little bit more, we have this diagram here where the black line is going to fit the data pretty well, but we can see that the green line here is significantly overfitting and trying to differentiate here between the blues and the reds. So the model here is learning the detail signal and the noise, and it's incorporating irrelevant information or the randomness in the data set. And what it is doing is it's using that to apply to new data. And this means that the noise or the random fluctuation of the training data is being picked up, and the model learns this concept by the model, and then it's turning around and applying that on new data, which means that it's not going to generalize very well. So we end up in a situation with Occam's razor, which ultimately would state that the simplest consistent explanation is going to be the best explanation. Therefore, the smallest decision tree that correctly classifies all of the training data is going to be the best one. Finding the smallest decision tree is actually pretty hard. So instead of constructing the absolute smallest tree that's going to be consistent with the training examples, we want to construct one that's pretty small. So we will go through some steps to identify some rules as to how we go about identifying a pretty small tree. Maybe not the smallest tree, but one that'll suit our purposes. And when we do this, it'll present some of our overfitting within our model, because ultimately a decision tree, if you leave it to its own end, is going to create the splits so that you end up with 100% purity in each of our leaves, or relatively homogeneous groups, which means, again, it's not going to generalize very well, and it's going to overfit the data, which again is going to be a bad thing for us because we're interested in how well it generalizes to new data. And so it's going to lead to low predictive accuracy in new data past a certain point. So sometimes you'll set the maximum number of splits prior to the beginning of your evaluation, just so that you don't let it go on forever. We've seen a chart similar to this before, where as we increase the complexity of our model, and in this case, the complexity is defined by our number of splits within a decision tree. We can see that for our training data, our errors will continue to decrease. But if the decision tree algorithm is left to its own on the training data, you see that it will get to a point where the error rate is 0, and then you have 100% purity. But that's not really what we want to do. We want to use the test data on unseen data to evaluate the error rate to do that. So to identify how much complexity is just actually enough. So what are some things that we can do to avoid overfitting? We typically fit a tree until we get 100% purity, and then the algorithms themselves start to prune it back. Pruning is a technique that's used to deal with overfitting specifically. So it's going to reduce the size of our decision trees by removing sections of the tree that provide little predictive or classification power. So you might start with something like this, and that you see here on the right, and then the algorithm will then start pruning back the chunks of the tree that give us low predictive power. There are different approaches that are used by different algorithms. So the cart decision tree method, for example, lets the tree grow to its full extent, and then it starts pruning it back. And then the idea is to find a point where the validation and the error begins to rise. And it's just similar to what we were looking at before here, where we are trying to find a point where it decreases to its absolute minimum, and then it starts to increase. So we're trying to find that point. It's going to generate successive smaller trees by pruning the leaves. And in each pruning stage, it's going to look at the multiple trees that are possible. And it's going to use that cost complexity to choose the best tree at that stage. So there's a cost function that is then being applied to identify what is the best cutoff point. The pruning process is going to yield a set of trees of different sizes and associated error rates. And then typically there's going to be two trees of interest. One that has the minimum error rate. And this one has the lowest error on the validation data. And then the best prune tree, which is the smallest tree within one standard deviation of the minimum error. And this adds a bonus for parsimony. So basically looking at the minimum and then what is within one standard deviation error of that minimum, and then selecting the tree that has the best optimal solution. Now, when we are looking at regression trees for prediction, we can use continuous variables or variables as our dependent variable. And then the procedures will be very similar to classification. You're going to look at many splits, and then you're going to choose the one that minimizes the impurity within each. So the process itself is essentially the same. You're just going to be dealing with continuous variables instead of classification variables. Regression trees are different from classification trees in that the prediction is computed as the average of the numerical target variable as opposed to a majority vote. So with prediction problems where you're looking at the averages, whereas the classification problem you're looking at the majority vote. The impurity measure is the sum of the squared deviations from the leaf mean. So it looks at the leaf mean and the sum of squared deviations, or the sum of squared errors. And then the performance measure is going to be the root mean squared error. Among the advantages of trees is that you can model either continuous or categorical variables, and it's going to be really easy to build through recursive partitioning, and it's just really easy to understand. It's going to be robust throughout the layers and misclassified data, and it produces rules that are easy to interpret and implement. The variable selection and reduction is also going to be automatic using the different algorithms that we can apply. So that's going to facilitate the execution of the model. It also shows the importance of the variables. So it's not, and it's also not going to require that any of the assumptions of statistical models are upheld. So from that respect, it's going to make it more of a non-parametric approach. And it can work with extensive handling of missing data. So if there's a lot of missing data, it will still be a robust model and work quite well. Among the disadvantages are that it tends to overfit the training data and may not perform well when the data structure is not captured well with horizontal or vertical lines. So if we cannot partition the data into nice little blocks and lines, it's not going to work as well. Since the process deals with one variable at a time, there's not really a way to capture interactions between the variables, which makes the trees unstable. So a small change in data can drastically change the model that you get. In summary, classification and regression trees are easily understood, and they tend to be a transparent method for predicting new records. A tree is a graphical representation of a set of rules, but a tree must be pruned to avoid overfitting of the training data. A tree does not make any assumptions about the data structure, but they do usually require a large sample size. So if your sample size is quite small, a decision tree may not be as effective. So be aware of that as you're selecting the type of model that you're using for your data.